and welcome to this video about the use of decision trees for regression. I'm going to illustrate the construction of such models using an example. Let's say we want to fit a decision tree to the dataset shown here. We have several options for this. A quadratic function might be a good choice. That's an example of a parametric regression model because it has a specific functional form. When you fit a straight line through a group of points using ordinary least squares regression, you're making assumptions that the functional form of the input-output relationship is linear. A decision tree, on the other hand, is an example of a non-parametric regression model which does not make any such assumptions. So let's see how a decision tree can fit this dataset. To begin, if we were to create the simplest regression model possible, we would just say that the model output is the average of the data as you can see in the image. Visually, this does not appear to be a good fit because the discrepancies between the data and the model predictions are fairly large. We could potentially do a little better by considering a split in the data. But where do I make a split? In general, you want to make a split so that the model predictions approximate the data optimally in some manner. In other words, you can create a split at x equal to 1 or 2.5 or any other location. In this example, that optimal value happens to be close to 4. Now, I'm going to compute the averages of the data on either side of the split. These represent my model predictions for different values of the input. Clearly, this is a better fit to the data than having no splits at all. So this leads us to the construction of a decision tree, which begins with a root node where we make a decision. This in turn leads us to the two leaf nodes. One of the leaf nodes gets 40 data points and the other gets 10. This is important because as we continue to keep making splits in the data, we will have fewer and fewer data points in each leaf node. Anyways, this is a one-level split in the data and appears to provide a better match than what we've seen previously. But let's examine what would happen if we consider an additional number of splits. I create another split within each leaf or each interval to create 4 bins. Again, the location of the splits is chosen to minimize the difference between the model predictions and the data. A split at x equal to 2, for instance, would not be optimal because the errors would have been larger. In any case, by creating an additional split, I'm going to grow the tree. I obtain 2 new leaf nodes on the left. Each of these leaf nodes has fewer data points than its parent. You can also visualize the growth of the tree on the right branch, creating 2 additional leaf nodes. So if one split in the data was good and 2 splits is better, then let's consider what happens if we have 3 splits. Again, choosing optimal locations to make that split, we will grow our tree some more. In each interval, we're going to compute the average of the data, and that represents the best approximation of the target variable for the specific input values. On the left branch, I have 4 bins and consequently 4 new leaf nodes. Each of those leaf nodes has fewer data points than its immediate parent. As you wait and see the right-hand branch growing to include more leaves, you will again observe very few data points associated with each leaf node. So, while the visual examination of this model indicates a really good fit to the data, in principle you want to formally validate your model using at least a train test split or k-fold cross-validation. I also do not want to give the impression that we could progressively keep increasing the depth of the tree and get increasingly better fits. Such a strategy may not work with realistic, noisy datasets. However, we can control the growth of a tree by specifying how many levels of splits we would like to see. This allows us to prune the tree to avoid overfitting to the data. We could also use other strategies for pruning a tree. So instead of just controlling the number of levels, we could also specify how many data points each leaf should contain. If I specify at least 5 points in each new leaf, several of the splits that you see would not have occurred and the tree growth would have been limited. I could also prevent additional splits in the tree if a leaf contains fewer than a specified threshold number of points. If I specify that number to be 10, then again, none of the splits in level 3 would have occurred because a split at that level would cause at least one child node to contain less than 10 data points. So to recap, a decision tree grows by making splits in the data. The location of the splits is chosen to minimize the difference between the model predictions and the actual data, and the tree grows till some criteria is met. Either we have fit each and every data point, which is likely to lead to overfitting, or we have pruned the tree to achieve a reasonable match to the data to allow the decision tree to make reliable predictions on new data. So with that background, let us look at the implementation of a decision tree in Python using the sklearn library. So in this Jupyter notebook, we're first going to take a look at the differences between parametric and non-parametric regression and why we might need non-parametric regression. As I discussed previously, if you use a parametric regression model, you are making an assumption about the functional form of the input-output relationship. It's either linear or you're going to be fitting, say, some kind of a polynomial. Now, with some data sets, we may not be able to immediately gauge what that relationship is. So let me show you an example. I'm going to plot a specific data set. And in this figure, we see the target variable on the y-axis. We see our explanatory variable or input feature on the x-axis. And if we do not know better, we'd think that this is a linear relationship and attempt to fit this data set with a straight line with two parameters, the slope and the intercept. But if you actually pay closer attention to the data, you can see that there's some cyclicity embedded within the data. So let's try fitting this with a non-parametric regression model. I'm specifically going to be using a decision tree regressor, and when I run this and fit this to the data set, we're going to be getting a model fit to the data. And in this case, we can actually see the cyclicity embedded within the data. Data that looks like this often cannot be fit with a parametric regression model, necessitating the use of non-parametric regression models. So decision trees are one such example. K-nearest neighbors are another example of non-parametric regression models, which we'll be taking a look at much later. So why is this specific model called a decision tree? It's called a decision tree because we are going to be recursively partitioning the data into various branches. These branches are going to lead us to leaf nodes, and those leaf nodes are going to lead us to additional leaf nodes. So as I continue to make various splits in my data, I'm going to keep increasing the depth of my tree. And at various levels, I'm going to be making decisions about where to make a split. And so that's why this is called a decision tree. So let's look at a very simple synthetic example of decision tree regression using the sklearn model decision tree regressor. I'm going to attempt to fit a data set that's specified by this quadratic equation with some noise in it. And I'm going to be using the sklearn model called decision tree regressor, but specifically I'm going to be restricting this to one level of splits. I'm going to fit this model to my data set, and I'm going to choose some test data, and make predictions on that test data. And finally, I'm going to plot the test data as well as my model predictions. Let's see how well the decision tree regressor with one split does. So in this plot, I have my target variable on the y-axis. I have my explanatory variable on the x-axis. The blue open circles represent the data, and the red line represents the decision tree prediction. Visually, we can see that this is not a good fit. But of course, in practice, we would have to run a train and test split and compare the performance of this decision tree with perhaps a slightly more complex model. So how do I increase the complexity of the decision tree? We've seen this before. I can increase the number of levels of splits. So if I were to try two levels of splits, then go through the same workflow, I'm likely to get a much better fit to the data set. And you can indeed see that in this specific figure over here, where again, I have my target variable on the y-axis. I have my input feature on the x-axis, and the red line shows the decision tree fit to the data set. Clearly, this is a much better fit than what we had previously. So again, one level of split is good, two levels of splits is better. So maybe three levels of splits could be something even better. Let's see if that is indeed the case. So with three levels of splits, we can see that our model fits the data with greater fidelity. So again, continuing with that argument, if three levels of splits is good, then maybe 10 levels are even better. So let me go back and change this parameter, which is called the maximum depth or the number of levels of splits, to be 10. And if I tried this with the number 10, then what we see is not an improved fit to the data. What we're seeing are symptoms of overfitting. This is a model that will likely not generalize very well to new data because it was overfitting the training data. So the question now becomes, what is an optimal number of splits? What is the value of the parameter max depth that I need to use to match this data optimally? Well, it turns out that that parameter is what's known as a hyperparameter. A hyperparameter is a parameter that you vary in order to get a specific model to fit the data optimally. Now, of course, we saw one hyperparameter, but there are several other hyperparameters associated with the decision tree that we'll soon be seeing shortly. But we also need to discuss something about regression metrics. If we want to compare one model with another, we need to have some quantitative basis for comparison. What we're going to be using in this specific example is known as the R-square value. And so while there are several different options for making comparisons with regression models, we're going to use the R-square value at this point in time because we all intuitively understand what the R-square value is. It represents a measure of how much of the variability how much of the variability in the data the model was able to capture. So in general, a higher R-square value would be considered to be better. Now, of course, there are several other regression metrics, and we'll be discussing those at a later stage. At this point in time, our basis of comparison is going to be the R-square value. So let me show you how we can implement a decision tree regressor and get the R-square values for our training and our test data set. We're going to make a split in the data. We're going to choose a test size of 20%, and this 20% is going to be randomly selected. We're going to fit a decision tree regression model with a maximum depth of 1, and we're going to plot the model and the data. And we've seen this before. This is clearly a less than satisfactory fit to the data. But what we're interested in is the R square values. So I can get the R square values for the model against the training data set, as well as the R square values against the test data set. So how well is the model fitting the training data after it completes the training process? And how well does the model fit the test data after it has been trained? So if we look at the R square values, we'll see that the training R square is 0.29, which is nothing to write home about. And the test R square value is 0.26, which is also quite small. And in this figure over here, what we're looking at is the predicted value of the target variable against the test values or the true values of the target variable from the test data set. The dashed line over here represents the 1:1 line. And if we had a perfect prediction, all of the data points would lie along that line. Instead, because we tried just one level of splits, we're just going to get two values for our target variable. And clearly there's quite a bit of discrepancy between what the model is predicting and what the data is telling us. But we were able to quantify the goodness of fit by uh, quantifying the R square values. Okay, so moving on. So what are the hyperparameters of a decision tree? I discussed this when we were talking about the previous example. We do have the maximum depth, which defines how many splits we're going to be making. The other hyperparameter which we discussed was the minimum number of samples required to split a node. So for instance, if a node or a leaf has 17 samples and the value of this hyperparameter is 20, then the tree will be truncated at that point and no more additional splits will be made. So in this manner, you can truncate the growth of a tree or prune a tree. The minimum number of samples required to be in a leaf or node is the next hyperparameter. So as we keep making splits, each and every leaf or node is going to get fewer and fewer data points. And we have seen this. So now if you want to prevent uncontrollable growth of the tree, we can specify a minimum number of samples required to be in each child or leaf node. If I specify this value to be 10, then we're never going to have any leaf that contains lesser than 10 data points. And so again, with this hyperparameter, we can control the growth of the tree. Between these three hyperparameters, we can balance the need to fit the data set while also allowing the model to generalize to new data. Now, of course, there are other hyperparameters that we should consider, but in this specific example, we just have one input feature and one target variable. So we're not going to be looking at feature selection at this point in time. So we're just going to focus on the three hyperparameters that I just discussed. So how do I make choices of these hyperparameters? Typically, this is going to come with experience, but for this specific data set, we've seen that 2 levels of splits or 4 levels of splits or maybe even 6 levels of splits probably is a decent choice. And given the size of the data set, we would like to have at least 10 or 20 or 40 samples for each and every node. And the minimum number of samples before you make a split, correspondingly, we choose some numbers. I'm choosing 3 different hyperparameters and 3 levels for each of the hyperparameters. It's not necessary that you choose only 3 levels for each hyperparameter. I can choose 5 or 6 or 7 different levels for each hyperparameter. For instance, for the minimum number of samples to make a split, I could have chosen 30, 40, 50, 60, 70, 80, and 90. And that would be 7 different levels. But nevertheless, given these 3 hyperparameters and the 3 levels for each one of them, if I were to evaluate how many combinations of hyperparameters there are, it would end up being 27 different models. So I'm going to be comparing 27 different models on the basis of their R square value fits to the training data set. I'm not just going to be fitting them to the training data directly. What I'm going to be doing is five-fold cross-validation. So in the next line, you'll see that I'm using five-fold cross-validation, and I'm going to be fitting each one of these 27 different models. So when I run this specific cell, it's 27 fits with five-fold cross-validation. So I'm going to get 135 different models. Keep in mind that with five-fold cross-validation, what we're essentially doing is randomly breaking up our data set into five folds containing 20% of the data. And I'm going to choose one of the folds to be my test data, and I'm going to train the model on the remaining four folds. And then I'm going to progressively keep changing which one is my test data and which of the other four folds are my training data. And in that manner, I'm going to get five different data sets to train on and five different data sets to test on. So I'm going to get five different model fits for each combination of hyperparameters for a total of 135. So if I run this, and this will happen fairly quickly because it's a relatively small data set, you can see that we have the model, we have the output of this run. For split 1 of 5, when I use the model with the maximum depth of 2, minimum number of samples for a leaf required to be in a leaf of 10, and minimum number of samples required for a split to be 40, I get an R-square value of 0.728. When I consider the second split in the data, I get an R-square value of 0.682. And likewise, as I go down this table over here, I'm going to be evaluating different models and I'm going to be getting different R-square values. But you can see that each model is evaluated 5 times because there are 5 different folds in the data. Then the next model is evaluated 5 times and so on and so forth down this table. So I can plot these results in with a little bit more clarity. So I have model 0 and its R-square performance against the first split, the second split, third, fourth, and fifth split. And I can also rank the model. This model is ranked 19th. And if I scroll down this table over here, you'll find that there's one model which appears to do better than the rest. It has an R-square value of close to 0.89 with split 1, 0.89 with split 2, with split 3, with split 4, and split 5. So what we're looking at over here is not just a high R-square value. We're also looking for low variability across the model fits for each one of the folds. We want our model to be to generalize to new data, which means that the model should not be sensitive to how the test data looks like. It should have an equivalent performance across all of the 5 folds or low variability across all of the 5 folds. But at the same time, it should also have a good R-square metric across the 5 folds. And that's what we see with the best model over here. We can see which one is our best model. It happens to be the model with the maximum depth of 6, minimum number of samples required to be in a leaf of 20, and the minimum number of samples before I make a split to be 40. So I'm going to confirm again that this indeed is my best model. So I'm going to apply this model to my training data set again, and I'm going to evaluate the model across 10 different folds using 10-fold cross-validation. And I'm going to ensure that this model is indeed the best model and demonstrates equivalent performance across each one of the 10 folds. So when I plot the R-square values on the y-axis versus the different folds on the x-axis, that is indeed what we see. We see an R-square value of close to 0.9 across all of the 10 folds and very low variability. This is a model that you would tend to trust because it performs equally well across all of the 10 folds with low variability. Or in other words, it's insensitive to the choice of test data and can generalize well to new data. All right, so given that, Let's go ahead and apply this model to my test data and plot my results. So we can see the target variable on the y-axis. We can see my explanatory variable on the x-axis. The blue open circles represent my data and the red dots represent my model fit. So visually again, we can see a significantly better fit to the data in comparison to what we were attempting to do manually by changing the hyperparameters manually. So grid search cross-validation allows us to evaluate multiple combinations of hyperparameters, and by specifying a certain performance measure, we can choose the best combination for our specific task or our specific data set. So that's largely what I wanted to share with you as far as decision tree regression is concerned. I do want to mention that there are a few other things we have not considered in the context of regression. One is the different types of regression metrics, and the second thing is something called residuals analysis. Residuals analysis is an important aspect of solving regression problems, but we'll come to that at a later stage. So, to recap, we began this Python notebook by attempting to fit a decision tree to a specific data set, and we changed the value of a hyperparameter successively from one step to another, and we got progressively better fits till a point where the fits got really bad and we were seeing overfitting. And that led us to ask ourselves the question about what are the best hyperparameters that I need to use to fit this data set. So that led us to a discussion of the various hyperparameters we can tune in the context of decision tree regression. We specified a few choices for those hyperparameters, and out of the 27 different models that we considered, we chose the best one, and the best one demonstrated the best performance across all of the 10 folds. It also showed the same performance across all of the 10 folds, meaning that it was insensitive to the choice of test data. So, this is an example of non parametric regression. For certain data sets, decision trees are going to be a very, very good choice. Thank you for listening to this.